Welcome back to the workbench of Hobby Paranormal, where we analyze paranormal technology and develop innovations for future exploration in the field of the paranormal. Today, our examination diverges from typical ghost hunting gadgets to focus on an instrument essential for constructing such devices. Recently, the company Neutri donated their static field meter FMX003 to the channel for review. It was a fortunate coincidence, as it was the exact piece of equipment that was needed for my current electronics project. Paranormal investigators rely on technological tools to detect energy fluctuations within the environment, often inviting entities to interact with the equipment to facilitate communication. Due to uncertainties regarding which energy will provide the evidence, a wide array of equipment is utilized in investigations, such as millimeters, tri-field, K2, tripwire, REM pods, and other devices that have a variety of sensors that can measure temperature, vibration, light, motion, and heat. However, in this video, the focus will be measuring and detecting electric charges. Electric charges can persist on an object for a long period of time, but the static electric fields cannot be detected by EMF meters. You will need a different type of sensor for that. Static electricity, commonly experienced as a shock when touching a metal object after walking across a carpet, is precisely the type of energy measured by this meter. Not only will it quantify the strength of the static charge, but also determines its polarity, distinguishing between positive and negative charges. I have a science kit for exploring static charges. It comes with 3 rods made from different materials: glass, acrylic, and ebonite. That's a material made of hardened rubber, and 3 different types of cloths: silk, wool, and cotton. The science kit suggests trying different combinations of rubbing the rods with the various cloths and seeing the results. I found the best results are from wool and ebonite and cotton and acrylic. A classic classroom science experiment that demonstrates the presence of a static electric charge goes like this. First, I'll show the ebonite rod is neutrally charged and cannot pick up these bits of paper. Next, I'll induce a static charge on the ebonite rod by rubbing it with a wool cloth. And finally, the rod is attracting the paper bits. I will perform the same experiment with the acrylic rod and the cotton cloth. The science kit is missing the ability to measure the polarity and quantity of the charge. Even though the results appear to be the same, the charges are, in fact, opposites. Let's bring in the meter to this experiment to measure the charges on these rods. I'll start with the ebonite rod and wool cloth to charge it up with static electricity. As I begin approaching the sensor, it detects about -1 kV. The analog meter at the top shows a lot of bars on the negative side. This is because the meter is in the low range of plus or minus 1.5 kV. But the meter switches over to the high range when it exceeds that. The high range is plus or minus 22 kV. The ebonite rod seems to measure around -6.5 kV. Next, I'll charge up the acrylic rod with the cotton cloth. This time the static charge is positive. The bars on the top are on the positive side of the meter. It's hard for me to estimate the distance, but I can see at one point it was reading consistently at plus 6.5 kV. Roughly the same voltage, but the opposite polarity than the ebonite rod. I will bring back the ebonite rod, and without charging it again, it has lost a little charge. Now it reads minus 5.7 kV, and the acrylic rod reads about plus 5.2 kV. As I mentioned earlier, EMF meters are unable to detect electric fields. Nonetheless, conducting a demonstration is still worthwhile. I have the following instruments on the workbench: K2, tri-field on magnetic setting, millimeter, hold to power. Then I'll turn off the temperature to put it in fast mode. And the REM pod. Oh, and if your REM pod gets stuck like this, you can press the REM 0 button next to the green LED. First, I'll demonstrate that these meters can detect a magnet. Each meter does as expected. The REM pod will not respond unless I get my hand too close to it. Now let's bring the electrostatic field meter in for this next demonstration. I will start with the ebonite rod and charge it up with a wool cloth to create a negatively charged object. The field meter reads minus 11.6 kilovolts. Let's see if any of these instruments can pick up the charge. As you can see, neither the K2, tri-field, mel meter, or rim pod sees the energy. I'll go back to the field meter to confirm if the rod still has a negative charge. Yes, about minus 10 kV. Next, I'll charge up the acrylic rod with the cotton cloth. This produces a positive static charge. Once again, I'll confirm it with the meter, plus 3.5 kilovolts. Not as strong, but sufficient. I will place the acrylic rod as close as possible to the instruments. And like before, you can see that nothing was detected by the meters or the rim pod. Out of all of these instruments, the only one that's here is the tri-field meter that has an electrical setting for checking stray AC electric fields. Let's set the other instruments aside. I will state for the record that there are other static detectors that I don't have in my collection that I would have liked to have included in this test. So I can't say for sure that these static detectors will detect both positive and negative charges. I will turn the tri-field meter to its electrical setting and try these experiments again. I'll charge up the ebonite to test the negative charge. I do get a reaction, but look how close I must be to the meter to get a reading. The detection drops off dramatically after even a couple of inches. Now I'll charge up the acrylic rod for the positive charge. In this case, there isn't any detection on the meter, even at point-blank range. Well, sort of. It's more complicated than that. You may notice that the tri-field meter sometimes detects the positive charge, but then not the negative charge. And when the charge is balanced, the meter can't see the positive charges anymore. This is because there's a capacitor as part of the detector's input for measuring AC, otherwise known as alternating current, like those coming from electrical equipment. What we have been testing are static charges that do not change or alternate polarity. Thus, the tri-field meter can't truly be used for this purpose. If you don't have a science kit but you'd like to try these experiments for yourself, you can use something that you probably already have in your house, a plastic hair comb. Assuming that you have relatively dry hair, if you run the comb through your hair a few times, you generate a negative electric charge. And the meter reads roughly negative 11.5 kilovolts. The tri-field meter has no difficulty seeing the charged comb. If you want an alternative method to generate a negative charge, it is possible to charge the comb using a piece of fake fur, like this one that I got from Hobby Lobby for a few bucks. It puts a negative charge on the comb. Although not as strong as combing the hair, the comb reads about negative 6.5 kilovolts, and the tri-field meter has no difficulty seeing the charged comb. Notice that when I wiggle the comb in front of the meter, that increases the reading. That is because the tri-field meter is designed to read an alternating current. Next, to create a positive charge on the comb, use a plastic bag or bubble wrap made from low-density polyethylene. Rub the comb with the plastic a few times, but sufficient to create a positive charge is confirmed by the static field meter, plus 0.86 kilovolts. Note that the tri-field meter does not detect the positive static charge unless I wiggle the comb in front of the meter. You may wonder, does wiggling the comb create an alternating charge? The answer is yes. It is truly creating an alternating current. Here's the explanation. All electrons have a negative charge, and there are electrons in the environment. A neutral charge is when the object has the same electrons on its surface as the surrounding environment. It's kind of like room temperature. When charging the ebonite rod with a wool cloth, that has the effect of adding more electrons to the rod. Thus, it has more net negative charge when compared to the surrounding environment. When charging the acrylic rod with a cotton cloth, that has the effect of removing electrons from the rod, and thus by removing electrons it will appear to have a positive charge relative to the environment. When we add motion, that net balance changes. A negatively charged object approaching the meter will have a negative reading, but that same negatively charged object, when retreating away from the meter, will have a positive reading. Likewise, a positively charged object approaching the meter will have a positive reading, and a retreating positive charge will have a negative reading. Advancing and retreating, positive and negative electrical charge on objects can be difficult to distinguish which is which. Thus, in our case, we only care if there's any disturbance in the electrostatic field. On the workbench, I have a DIY electrofield detector, and there's something not quite right with the way that this works, but I think it's very interesting to see how it works. Over here on the output, I have this orangey yellow LED. That's the reset button. I got to reset it because I touched the field. The red lights up here are positive, and the blue lights down here are negative. And so in the middle is 0. And they're independent. The red can move independently than the blue. And that's very important because what I'm going to show you is something very interesting. I have an ebonite rod and a wool cloth. It's already reacting to it because I've charged them up again, but to show this, so I bring it close, it's a pretty good charge. About 12, I saw 12 in there. And you'll notice that right away that an advancing ebonite rod will detect the blue, but also it's an advancing negative charge also means that it's less positive. In other words, in physics, we can't determine whether or not it's a negative that's advancing on this side of the circuit, or if it's a negative that's retreating. Same thing with the positive. We can't tell when the positive is coming closer to us, it's just less negative. And when it's retreating, you can see what's happening here. This is a positive rod, but when I'm going away from it, so what's happening is that the components that I've used here, the JFETs, are like a memory cell. They'll memorize the charge on it. Once enough charge is accumulated on it, it'll keep the JFET open. When I push the reset button, it discharges that charge on the gates of these JFETs. And so now it'll work properly. A positive will detect a positive, but as soon as I retreat the positive charge, the negative one thinks it's a negative charge that's advancing. So it got me thinking that perhaps what we should do, instead of trying to detect like this meter does, a positive and a negative, maybe what we should be doing is we should be detecting any kind of movement, positive or negative. It doesn't matter if if a positive is advancing or it's retreating and it's doing the positive or the negative. We can do either one. We're just interested in movement. So we don't have to replicate exactly what this meter does. So I'm going to now tear down the circuit and I'm going to build it again. This time with the idea that we want to have any electrostatic field detection. We also want to prevent this function called latch up on these JFETs, because when they latch, we've seen what happens. And even though the charge is now gone, this still stays on there. And if you have this on a ghost detector, you can say, well, and I've touched it. You can see how confusing it would be trying to figure out, well, should I hit the reset button or This project is still a work in progress. It has shown promise that electrostatic field disturbance detector is possible. It will take some more research and development. Please stay tuned. I will post an update video when progress is made. Let's take a moment to consider the implications of all this, and perhaps you've already begun to form your opinions based on what you've seen so far. These demonstrations have revealed a blind spot. If all you're using are EMF meters, these instruments fail to detect static electric fields. They completely miss the evidence. Let me ask this question. How important is it to be able to detect static fields during your investigation? Have you or somebody you know experienced things like they've walked through spider webs when there were none, or out of the blue a strange tingling sensations come over them, or did the hair stand up on the arm or neck for no apparent reason? Those sensations might have all been caused by static electricity. Let me know if you're using static electric meters in your investigation, and if so, what types and do they work well in getting evidence? Please drop a comment down in the comment section below. I'll be producing more videos like this, so please like and subscribe. Thanks for watching.